In this video, we're going to look at a data structure called Deque or Deque. So rather than tell you what is Deque or what does this data structure do and how to use it, I would like to go over a Leetcode problem, and then we can go over why we should use a Deque and what kind of problems we're using this data structure to solve. So you can see here, this is our Leetcode problem, sliding window maximum. So we're given an integer array. There's a sliding window of size k, which is moving from the very left of the array to the very right. You can only see the k numbers in the window each time the sliding window moves to the right by one position. So return the maximum sliding window. So you can see here we have an integer array, and the k, in this case, our window size is 3. So you can see here we basically slide our window throughout the array. For each and every single time we slide our window, we basically want to get the maximum value, right, within our window. So you can see here the maximum value within our window is 3. And then here the maximum value is still 3. The maximum value in this window is 5. The maximum value in this window is 5, and so on and so forth, right? And then what we're going to do is that we're going to get those maximum value, right, and then return that in array form, right? And you can see that in our integer arrays, we could have duplicate values, we can have negative values, right? And so basically you can see that this is basically the problem that we're trying to solve, right? And you can see here the constraints. Like I said, we can have negative values, and the k is always going to be smaller than or equal to nums.length. And for each and every single, so basically for the array, we're going to ensure that we have at least one element in the array. And then basically we want to be able to solve this problem, right? So in this case, to solve this problem, one way we can do it is we can be able to use a brute force approach, right? So while we slide our window, for each and every single window that we're in, we can just iterate k number of times to figure out the, in this case, the maximum value, right? But that will give us a time complexity of big O of n times k, right? And this number of elements that we have in our array, and the k is basically the input window size, right? So in this case, how can we be able to further optimize this solution? Well, another way we can do it is we can be able to use a binary search, right? Or a binary search tree, because we know that for binary search tree, the insertion and deletion is always going to be log, right? It's always going to be log. So in this case, we're just going to create a binary search tree with the size of k. So this will ensure that the time complexity for insertion and deletion is always log k. But in this case, we're iterating the entire array. So the time complexity is going to be n times, so big O of n times log k, right? So in this case, we basically just going to use a binary search tree, right? And then we basically going to put the values, right, a balanced binary search tree, and we're going to store the values in a binary search tree. And then if we want to find the maximum value, we know that the maximum value is always going to be the very, very far right, in our tree. And then if I want to delete an element, in this case, if I want to find it, I can basically perform a login complexity, right? Login time complexity to find the element, since we're using a binary search tree. And in this case, all the elements that are less than the current node's value will be at the left. All the values that are, or all the node's value that are bigger than the current node's values on the right side, right? So that's also another approach. But in this case, how can we be able to further improve the time complexity? So let's say we have an example like 1, 2, 3, 4. So let's say k is equal to 3, and then our window is right here, right? So in this case, we iterate each and every single element in our window. In this case, their largest value is 3, right? Because in this case, we visit 1, and then 2 is bigger than 1, and then 3 is bigger than 2, so therefore the largest value is 3. But then once we visit our next window, right? In this case, we delete the last element and then expand the right element. In this case, we can see that we basically have to iterate the table again, or the window again, right? So 2 is smaller than 3, 3 is smaller than 4, so therefore the largest value is 4 in this window, right? But the thing is that you can see there's a lot of duplicate works that we're doing, right? Because you can see that if we already visit 2 and 3, right, we already checked that 2 is smaller than 3, right? Then in this case, we don't have to do this duplicate work. All we have to do is we have to check the previous window's largest value, right? In this case, the previous window's largest value is 3. So if we were to expand that window, we check to see if the current element is actually bigger than the previous window element. If it is, then in this case, we don't have to check those elements at all, right? So in this case, that's what we're trying to do, is that we can be able to use a data structure like Deque to be able to solve this problem, right? And then you can see here in our Deque data structure, you can see here we have our Deque, right? And then we can use array Deque or linked list. And then for Deque, it's basically has this ability of append first and delete first, as well as append last and delete last, right? If I append an element in our queue, right, I can append to first, and I can also delete first, right? So, and I could also offer last, basically append from the tail node, right? And then I can also basically pull last, which basically deletes the last element out of the queue, right? So you can see that it has the ability of both stack and queue, right? So what we can do is that we can be able to use a data structure like this to be able to solve this problem, right? What we can do is that we can basically, just like what I mentioned before, like the 1, 2, 3, 4 example, right? So we can have our Deque like this, that we want to be able to do this in a descending order. So in this case, if 1 is smaller, right? If it's smaller than the previous element, if the element that we're going to add it, in this case 2. So in this case, we don't have to add 1 onto our queue, right? So we can just leave 2 here. And then for our next element, in this case 3. 3 in this case is actually bigger than 2, right? The previous element. So in this case, we can just delete 2 and then just like add 3 here, right? And then in this case, if I want to know the maximum value in our current window, which is basically the first element in our queue, right? In our Deque. So once we slide our window to the right, we check to see if the current element in this case is 4. 4 is bigger than the previous element, so we just remove this element and then we add the current element onto it, right? And we can be able to do this. And now let's try to go with a bigger example like this, right? So we're going to use a Deque. And what's going to happen is that our Deque is going to have a descending order. So we're going to have the largest value at the head node, right, towards the first elements, and then small values will always be at the last, right? So what's going to happen is that we're gonna basically try to use a Deque, try to avoid those duplicate computation, right? We don't have to basically iterate those visited values to compute the largest value. All we have to do is we can use a Deque, try to be able to do this in a constant time, right? We know that the Deque, if we want to look a element, right, the first element or the last element, right, we can be able to peek, we can be able to pop the first element or the last element in a constant time complexity. So what's going to happen is that first we have 1, we add 1 onto the queue. So once we have 3, in this case, just like I mentioned, right, we want to keep the largest value, right? So in this case, 3 is bigger than 1, so we remove the first element, right, and then we add 3 onto it, and then we have -1. So notice that I said we want to do it in descending order for our Deque. So in this case, if I have -1, I can still add it onto our Deque, right? So in this case, we have our -1 onto our Deque. And then if I want to know the maximum value within our window, right? So in this case, it's going to be the first element, okay? And then what's going to happen is that we have to shift our window 1 to the right, okay? So once we shift our window 1 to the right, so you can see we have this, right? So what's going to happen is that we're going to also have to delete the left element, right? In this case, we check to see if the left element is actually the first element that we have in our Deque. If it is, we delete it. If it not, we continue, right? So you can see here, we can be able to use a Deque to keep the maximum value in order, okay? So for our next window, in this case, if we want to know the maximum value, it's basically still the first element, right? But first we have to add a -3. So we add -3 onto the Deque, right? Because -3 is smaller than -1, right? If it's bigger, then that's not going to happen. Then we have to delete the elements until we find a correct position, right, for -3. So in this case, you can see here the maximum value is 3. So in this case, we basically is the first element in our Deque, right? So what's going to happen is that we're going to shift our window one to the right. And so to do that, what we had to do is we basically going to basically add the next element, and then we have to remove the element that's on the left pointer, right? And then we have to shift the left pointer one to the right. So in this case, 3, right, is basically the left element, right? So in this case, we have to remove 3. Okay, and then we have to add 5, right? In this case, 5 is bigger than -3, right? And then 5 is also bigger than -1. So in this case, we have to delete those elements, right? And then we can be able to insert 5 onto the Deque, right? So for this window, we know that the maximum value will be the first element in our Deque. So in this case, it's 5. So we basically save that here. And then what's going to happen is that we're going to shift our window one to the right. So what's going to happen then is we're going to have our window like this. So in this case, we delete the last element, or the left element, in this case, -1. -1 does not equal the first element in our Deque, so we don't have to touch the Deque. And then we have 3. 3 is smaller than 5, so we add this onto our Deque. Okay, so what's going to happen then is if I want to find the maximum value, it's just basically the first element in our Deque, which is 5. And then we shift our window one to the right. So in this case, the element that we're going to shift, right, the left element is -3. -3 does not equal the first element in our Deque, so we don't have to touch our Deque. And then we have 6. 6 is bigger than all of those values. So we have to continue to remove or pop the last element, right, out of it until we find the correct position that there is no elements, or the current element or the top element on our Deque is actually bigger than 6, or there's no elements at all, right? So now you can see all the elements are smaller than 6, so we add 6 append onto the Deque. So what's going to happen then is that if I want to find the largest value, which is basically the first element in our Deque, right? So then we shift our window one to the right, and then we have 7. 7 is bigger than 6, so we just basically remove 6, and then we add 7 onto our Deque. So then what's going to happen is that 7, right, in this case is basically the largest value, because 7, in this case, Deque is at the first. And then we will have to, in this case, shift our window one to the right. So in this case, we have to delete the left element, in this case 3. 3 does not equal to 7, so in this case, we don't have to touch the Deque, right? Here, the code, I basically create a Deque, and I have a left and right pointer, and I have a result that we're going to, a result list that we're going to return at the end. And basically you can see I basically iterate each and every single element in the result, convert it into a integer array. So what we're going to do is that, just like the any other sliding window videos that we did, we first check to see if right is less than n. If it is, then we basically first expand our window, right? But first we have to check to see if Deque is not empty. If it's not empty and the previous element, right, peak last. So we take a look at the previous element, and then we check to see if that element is less than numset right. So if it is, we have to remove that, right? So we want to make sure the Deque is in descending order, so we have to check the previous element. And then what's going to happen is that we're going to add position, right? We're going to insert this current element onto the Deque. So once we've done that, we now have to shrink our window, right? So we first check to see if our window is at the correct size, right? If it's, in this case, if it's equal to n, then what's going to happen is that we're going to get the maximum value, right? Which is basically the first element in our Deque. And then we update the Deque, right? We will have to be able to shrink our window, right? So in this case, if the first element in our Deque is actually equal to the left element, then what we have to do is we have to remove the first element in our Deque. And of course, we have to move our left pointer one to the right, right? And then we have to also move our right pointer one to the right as well. And then at the end, you can see that this is basically how we going to slide our window throughout the array. And then we're going to use the Deque to be able to perform these operations in a constant time complexity. So you can see that the only time complexity that we have in our algorithm in this case is basically big O of n, where n is the number of elements that we have in the array.